Hello and welcome to My AP Videos. In this segment, topic 6.5, we're going to look at the energy of phase changes. We've chosen water as our substance and we'll be looking at the energetics that are involved in the various phase changes and temperature changes that it undergoes. My name is Harry Breelman. I'm from Guilford High School in Guilford, Connecticut, and I'm so pleased to be here. Let's consider some ice and let's turn it into steam. This is a phenomenon that I'd like you to observe, and I'd like you to think about the 5 consecutive energetic processes that will be occurring. Let's go ahead and take a look at it. This is time condensed, so it's going to take place very quickly. And there it is done. Let's watch it again. 5 things are occurring consecutively. I'd like you to think about what those are. And there we go. Okay, I see a ton of steam coming off. I could see the ice cube in there simultaneously. That's interesting. All right, so let's take a look at some of the processes that are involved. You're probably thinking about things like ice, liquid water, melting, boiling, things like that. And I've shown that diagrammatically down here. Now, it turns out that it takes 2,260 joules for every gram, that's about 20 drops, of water that you boil, that you turn into a gas from a liquid. Similarly, it takes 334 joules to melt a gram of ice. We refer to these as and watch the arrows, standard change in enthalpy of vaporization for boiling, and the standard change in enthalpy of fusion for melting, where enthalpy is simply the heat at constant pressure. Notice this is an open system, it's not sealed up, so we can use the term enthalpy rather than heat. Okay, so let's work our way up and down the ladder. Imagine that ice, we heat it up, it requires 334 joules per gram. That's called endothermic. Heat's going into the system. It then boils. Well, there's going to be some temperature changes too, but we'll get to that in a minute. That requires a lot more energy, 2,260 joules per gram. Again, endothermic. But we can go in the opposite direction. We can condense that steam. That should release energy to the surroundings to the tune of 2,260 joules per gram. And we can, of course, freeze that water, and that will release. Isn't that interesting? Freezing releases energy, 334 joules per gram. Let's consider a problem. It says here, how many nutritional calories are required to heat 18 grams of water from minus 20, I guess it's in the form of ice, to 110 degrees Celsius? That sounds like steam. If you want to pause this video and consider it before we move on, go ahead. I'm going to solve it in its entirety, and we're going to do a different problem on the next slide. Okay, I imagine 5 things happening. Minus 20 to 0, right? Yeah, minus 20 to 0, the ice will get warm enough to melt. Then it go all the way up to 100 where it will boil, and then it will get even a little bit hotter in the form of steam, and those should be our 5 steps. We have values for each of those steps when we need them. For any phase changes, we need to know how much energy is involved. Those are shown here and here. And for any temperature changes, we need the specific heat of that substance. Now, you might think it's just one number because it's water. Turns out there's a slightly different specific heat for ice, liquid water, and steam, and they're shown here. So we should have enough data now to solve it, and let's remember to change from joules to nutritional calories at the end. Okay, so first we're heating up from minus 20 to 0. Anytime we have a temperature change, we can use Q equals mc delta T, where Q is the heat in joules, m is the mass in grams, C is the specific heat, also known as the heat capacity, in joules per gram degrees Celsius, and delta T is the change in temperature in degrees Celsius. Now, I didn't write the units, but I'll say them out loud. We have 18 grams of ice. The specific heat is, check out, there's the one for ice. It's not 4.184. It's 2.03 joules per gram degrees Celsius, so grams is canceled. and we have joules per degree Celsius. And it's 20 degrees Celsius, so the temperature cancels at this point, and it does give us joules, 731 of them. We are now warm enough for that ice to melt. That requires 334 joules per gram, and we have 18 grams, so we have to put 6,012 joules into the system to do that. Now it continues to heat, and as you might have seen, it's doing it simultaneously because of some of the kinetics, right? Some of the kinetics are such that step 2 or step 3 begins while step 1 is still occurring. Isn't that interesting? Is that a Boltzmann distribution? We now are heating it from 0 to 100 degrees. Now that is a temperature change, so we still have 18 grams. We're now at 4.184 joules per gram degrees Celsius for our specific heat, and we're doing the entire 100 degrees Celsius, bringing us, adding to this another 7,524 joules into the system. But we're not done because we're now hot enough to boil. That requires 2,260 joules per gram, and we do have the entire 18 grams that has to boil. Now I say that way on purpose because did you notice in the video that the steam kept going forever? And this is the most energetic component. Over 40,000 joules are required. Students sometimes say, I wouldn't expect it to take that much energy just to boil, just to undergo the phase change. And maybe when you realize, as was shown in this video, that it's not just boiling, it's boiling to dryness, meaning every gram is leaving the pot. That might help you understand why that's the most energetic component. And the steam, of course, can get a little bit hotter. And for this, it's temperature change, so still 18 grams. This time we'll choose 2.01 joules per gram degrees Celsius. Since it's steam, it got 10 degrees hotter, and we have another 3,618 joules for a total of 58,565 joules, but don't forget we need nutritional calories. There are 4,184 joules in a nutritional calorie. This checks out at 14 nutritional calories. I always like to do that because it kind of gives you a reference point. Most people are pretty familiar with nutritional calories. Joules, not so much. 14 nutritional calories. What is that? Like eating a couple of potato chips? So it would be the amount of energy required is similar to the amount of calories you gain when you eat a couple of potato chips. It's really, by my way of thinking, it's really not that much. Okay, great. Let's solve a few problems related to these topics. Let's imagine that this time we have 36 grams of steam. We're going in the opposite direction, right? We're hot at this point. We want to cool it down from 110 to -5 degrees Celsius. Now for this one, I strongly recommend that you pause the video, solve it yourself, and let's give the answer in joules. First, let's consider the 5 consecutive processes that occur. And you would need that to solve this problem. And I've shown it visually here. We're starting with steam. It has to cool down to 100 degrees, which is cool enough to condense. It can then, as liquid water, keep cooling down in your freezer, let's imagine, from 100 to 0 degrees Celsius, at which point it will freeze. And it's a funny process. You might have seen those videos where that nucleation process is very unpredictable when it will actually freeze. Sometimes you open up your freezer in the morning and it hasn't frozen, but when you give it a little tap, it suddenly freezes. They call that nucleation. We can still get colder, and there you go. We have our 1, 2, 3, 4, 5 steps. Great. Let's go ahead and calculate that energy, starting at 110 and working our way down to -5. Well, we've got steam that can cool, and I've shown the whole thing here. I hope you did pause this and got this value. So it's a temperature change. Everything's negative this time. It's probably more convenient just to keep everything positive and then say that much amount of energy was released. But you can go ahead and use your negative values throughout, as I did. We've got 10 grams this time. There is the specific heat of steam, and it's cooling by 7 degrees, so we're putting that much in. It then condenses, which releases 22,000 plus joules. It then cools all the way down from 100 very hot water to water that's ready to freeze. That's the another big one right there, 4,184 joules. It's the condensation this time, the second step, not the fourth, that is the most energetic here. Then it'll freeze. That requires 3,340 joules, since we have 10 grams at 334 joules per gram released. And it can get a little bit colder. In this case, we're getting 10 degrees colder. And so for this amount, where we have I picked 10 grams throughout, so I'm not going to change it, but I think I'll change this later. It's 10 grams that this was solved for rather than 36. Regardless, that is the amount of heat for 10 grams. Now let's go ahead and draw this process as a function of energy versus temperature. So go ahead and put the temperature in the y-axis, the energy in the x-axis, and try to draw what's going on. Pause this video and go ahead and solve it. You should have that we've gone downhill and we have some diagonal lines and some flat lines, right? Anytime we are changing temperature, it's obviously diagonal. In this case, it's from 110 down to 100. At that point, it hits 100, and we have to go ahead and condense that down all from steam to liquid water. That's an isothermal process, meaning it takes place at 100. Now we can go all the way down from 100 to 0, and I think if it was 110, that would be only there because this should be a much bigger diagonal line, the whole 100 degrees. And then at that point, you have gotten down to 0 degrees and you're ready to freeze. So it will freeze at some point. That's an isothermal process. As each molecule is doing that, changing from a liquid to a solid, it's releasing 334 joules for every gram. And then you have ice, which is going to get, in this case, 5 degrees colder, and that would show that there. Okay, let's review. We've taken a look at really two things, temperature changes and phase changes. Temperature changes usually involve using a Q equals mc delta T formula. Phase changes involve just how many joules per gram it is. When these things get tested, they may ask for the process going uphill, meaning you're heating it. They may ask it for a downhill, you're cooling it. They might not do all 5 steps. They might do 2 or 3, where based on the melting point and the boiling point, you have to figure that out. By the way, the melting point and the boiling point are exactly the same number as the freezing point and the condensation point, right? They just involve one going through it uphill, the other one going through it downhill. And sometimes students find that a little bit confusing, but it's true. We also took a look at how we can graph this energetically and how we can show each of the steps. So that's a little bit about energy and phase changes. Note that these are physical processes. We can do similar things for chemical processes as well. This is Dr. B. Thank you for listening to this video.